A bee is flying home right now, loaded with nectar, doing everything right. It avoided the spider webs, ducked the birds, found the flowers, but there's a threat it never sees coming, because this one doesn't wait on a branch or hide in a bloom. It waits in open air, already moving, already locked on. The robberfly doesn't chase. It intercepts like a missile that picked its target before the bee even knew the sky was dangerous. And what happens next is one of the most efficient acts of theft in the insect world. Picture the bee on its way home. It cleared the spider webs, avoided the birds, found a good patch of flowers, and filled up completely. From where it sits, the flight path back to the hive is clean. No obvious threats, just open air and a straight line home. But a loaded bee doesn't fly the same way an empty one does. It flies lower, slower, and in a much more predictable line because the weight of the nectar pulls at it, and it's burning more energy just to stay on course. It can't help that. The weight changes everything about how it moves through the air, and that change is visible to anything that knows what to look for. Now consider what that bee actually represents at this moment. It spent the whole morning finding flowers, collecting, and now it's carrying the result of all that work inside its body. It's the most calorie-dense moving object in the air right now, and it's flying a steady, readable path. The success of the foraging trip is exactly what makes it a target. It paid the hard energy cost up front, and something else is about to collect the return. This kind of strategy shows up across the animal world. Frigate birds harass other seabirds in the air until they drop their catch, then grab the fish before it hits the water. Bald eagles do the same thing to ospreys. The pattern is always the same. Let another animal do the foraging work, then intercept the result. Biologists call this kleptoparasitism, and it keeps appearing across species because the math keeps working. A frigate bird that steals a fish spends far less energy than one that dives and hunts from scratch. So zoom back to our bee. It's heavy, it's predictable, and somewhere nearby, something has already read its flight pattern and decided the approach is worth making. The bee's threat model covers webs, flowers, branches, and birds. It doesn't cover open air, because open air always felt like the safe part. That assumption is precisely what the robber fly was built to exploit. How does a fly outmaneuver a bee that's been flying its whole life? It doesn't, actually. Not in a straight race, but that's not the problem the robber fly is trying to solve. Robber flies are interceptors. They don't sit on a branch and wait for something to land close enough to grab. They pick a position out in open air, watch the traffic moving through it, and calculate where a target is going to be, rather than where it is right now. That's a completely different hunting model, and it changes everything about how the attack unfolds. The robber fly watches multiple insects moving through its range and picks based on what it reads in their flight. A bee flying heavy and slow with a full nectar load is a much better return than a fast, empty one. So it waits. It burns almost nothing just holding position, and it lets the prey come into range on its own flight path. When it finally moves, it doesn't chase from behind. It commits to a point ahead of the bee and flies to meet it there. Not a pursuit, a prediction. Now consider the physical side of this. The robber fly's legs are covered in stiff spines, and they're built to close around a moving insect at speed and not let go. There's no second attempt if the grip fails, because both animals are in open air with no surface to reset on. The legs close like a trap on first contact, and that's the only contact there is. The whole strike happens fast enough that the bee's nervous system hasn't finished registering it before the grip is already locked. Speed isn't just an advantage here, it's the whole point of the interception model, because a slower strike gives the bee time to change direction, and the intercept math falls apart. What the data shows is that robber flies actively select prey that's already done the foraging work, targeting loaded bees specifically because the caloric return is higher and the risk is lower than going after faster, unencumbered insects. It's not random aggression. It's a selection process that runs before the fly, ever leaves its perch, the bee is caught. Mid-air, no surface to push off from, no branch to brace against, and the robberfly doesn't pause. The proboscis goes in almost immediately. A rigid, needle-like beak that finds the soft gap between body segments where the exoskeleton thins out. It's precise because it has to be. The bee is still alive at this point, and the robberfly knows it. What goes in through that needle isn't just a puncture. The robberfly injects saliva loaded with neurotoxins and digestive enzymes at the same time, and the neurotoxins hit the nervous system fast enough that the bee stops coordinating movement within seconds. It's not dead. It just can't fight anymore because the signals between its brain and its legs aren't getting through cleanly. The digestive enzymes start working at the same moment. They break down muscle, organ, and soft tissue while the bee is still technically alive, converting everything inside into liquid. The robberfly isn't chewing anything or processing food internally. It's running digestion inside the bee's own body and then drinking the result. The bee becomes a container. Now consider what's actually in that container. This bee spent the whole morning collecting nectar, so the liquid the robberfly drinks isn't just bee tissue. It's bee tissue plus a full nectar load, 2 food sources returned from one strike. From a pure energy standpoint, targeting a loaded forager returns far more than targeting an empty one, and the robberfly's selection process, back on that perch before the strike, accounted for exactly that. The whole process takes a few minutes. The robberfly holds the bee, lets the venom and enzymes do the work, feeds, then drops what's left. What falls isn't really a bee anymore. It's a dry shell, hollowed out completely. Across the family Acylidae, this feeding method runs consistent enough that researchers use proboscis structure and venom chemistry to sort species within the group. The needle isn't just how the robberfly kills, it's how the robberfly eats, a digestive organ that operates outside its own body, deployed on contact. Step back from the attack for a second and look at what actually happened here, because it's really just a transaction. The bee burned calories all morning. It flew out, searched for flowers, collected, and flew back on a tight energy budget where every minute in the air cost something. The robberfly held a position for a few seconds, then spent a fraction of a second striking. Same calories at the end, completely different cost to get them. This is what energy arbitrage looks like in practice. Arbitrage is when you profit from the gap between what something costs in one place and what it's worth in another, without doing the underlying work yourself. The robberfly found that gap between the cost of collecting food and the cost of taking it, and its entire biology runs inside that gap. That's why kleptoparasitism keeps showing up across the animal world. Frigate birds harass other seabirds until they drop their catch mid-air, then grab the fish before it hits the water. Bald eagles do the same thing to ospreys. Cuckoo bees lay eggs in other bees' nests, so their larvae consume the stored food without ever foraging. The scale changes across all these animals, but the math doesn't. Taking costs less than finding, so the strategy keeps getting selected for. Now, the robberfly isn't a broken or lazy version of a normal predator. It's a specialized one. Its spiny legs, its venom, its habit of watching from open air, its preference for heavy-loaded bees over fast, empty ones, all of it points at one specific solution. Find the animal that already did the foraging work, then convert that effort into your own meal. Nature doesn't reward effort, it rewards outcomes. A robberfly that intercepts a loaded bee pulls the same caloric return as a bee that spent the whole morning at flowers, and the robberfly spent almost nothing getting there. Over a lifetime of meals, that difference compounds into a serious survival edge. The bee did everything right by its own rules. It just didn't know there was a predator whose whole strategy depends on bees doing exactly that. That the bee never saw it coming because it wasn't looking up. It scanned for webs, watched for birds, stayed clear of anything that moved on a surface. Open air felt safe because nothing in its experience said otherwise, And that assumption held right up until it didn't. Sit in a meadow long enough and you start to see this pattern everywhere. Every animal that forages is also a target for something that doesn't bother to forage at all. Evolution keeps filling that gap because the energy math keeps paying out. Next time you watch a bee working a flower, consider who else is watching.